today use the transfer matrix method to arrive at the transmission loss of the expansion chamber muffler. Remember in the last class we talked about how to get it in the usual wave propagation scheme of analysis. As remarked in the last class, we are going to redo it in a little more elegant fashion using the transfer matrix method. And where we left last time is that we defined a new kind of impedance which is more adapted to the scheme of duct acoustics, with changing area of cross section and so on, wherein the impedance is in terms of mass velocity. So, it is again the ratio of acoustic pressure by velocity, but the velocity has to be understood as a mass velocity rather than as the particle velocity. Okay. So, towards this end you will recall that characteristic impedance for a plane travelling wave, characteristic impedance for a plane travelling wave that is the P by U was equals to rho naught C, U being the particle velocity, right. But in terms of this modified impedance, the characteristic impedance will read as modified for plane travelling waves we know that the two impedance are related by this condition, that we have to divide traditional impedance by rho naught S, S being the area of cross section, right. So, if we do that we will get rho naught C divided by rho naught S. So, C by S is the characteristic impedance in this new definition for the plane travelling wave, right. We will just abbreviate this by Y. So, this characteristic impedance is denoted by Y. So, when we say capital Y from here on, it means C by S, right. This is, remember, for the plane travelling wave characteristic impedance, this is not for a standing wave situation. Okay. And similarly, we will define the acoustic mass velocity will denote by V. Okay. So, V stands for the mass velocity, U stands for the particle velocity, and V is, as we had said, rho naught S U. Okay. So, that is how we are going to change a few notations from here on. Okay. Now, let us look at the geometry. Okay. So, it is infinitely extended in both sides, and this expansion chamber is of length L, and the area of cross sections are S1, S2 and S1 again, and we have taken S2 by S1 to be equals to n, which is greater than 1. Okay. So, this is our geometry. Now, we wish to relate the, as I said, the transmitted wave amplitude to the incident wave amplitude in this case. So, what happens in transfer matrix method is that we are going to look at individual pieces of this duct, and we are going to construct a few hypothetical stations. So, this is the downstream station, the station just upstream is this, and then you have this station, and then you have this station. So, we have this as our station 1, this is station 2, this is station 3 and this is station 4. Okay. And transfer matrix relates the state variables between each of these stations, as simple as that. So, instead of trying to solve for in one shot the entire 4 by 4 system or no matter how many variables you have, the approach is different here. We are simply going to construct transfer matrices which relates the state variables between each of these stations, right. So, first we are going to relate how P2 V2 is related to P1 V1. So, at station 2 we are the elementary quantities of interest are the pressure and the mass velocities. We are going to talk in terms of mass velocities. Okay, so, we are going to relate the upstream pressure to the downstream pressure and the upstream velocities to the downstream velocity. Again I iterate, when I say velocity from here on, it does not mean particle velocity, it means mass velocity. Okay. So, we need to relate all the upstream and the downstream quantities with a certain matrix, because upstream there are two states, I mean every station there are two states, pressure and velocity. We need a relation relating the two, right. So, the equation relating P2 and P1 V1 is P2 equals to P1, that is it. Okay. So, it is 1 0. Similarly, V2 is equals to V1, remember that is why we changed over from particle velocity to mass velocity. V is the mass velocity on both sides is just the same. So, this is just an identity matrix, no big deal, right. Similarly, it is easy to see that P4 V4 is same as P3 V3, just the same thing is happening, right. P3 V3 is 1 0 0 1 and P4 V4. So, the pressure and velocity on either side of the expansion point and the contraction point is just the same, velocity meaning mean velocity. All that remains is to relate between 2 and 3. So, P3 V3 has to be related with P2 V2 also, and we need to derive this matrix. We will call this for now T11, T12, T21, T22. Okay. So, this is the generic form of a transfer matrix. Each of these matrices that we have derived are basically transfer matrices which relates the upstream and the downstream state variables. The state variables in this parlance is just the pressure and velocity. It is slightly different from state variable concept in a dynamical system. Here remember we are talking with the harmonic assumption. So, when I say state variable, it means pressure and acoustic mass velocity. So, transfer matrix is relates the P n minus 1 V n minus 1 states to P n V n states. P n minus 1 V n minus 1 is the downstream and P n V n is the upstream. Actually upstream downstream at present does not make much sense, but none the same we understand that the incident is from the left side and the transmission is from the right side, right. So, we are going to number it such that at the end it is going to be 1. Okay. The point where the transmission will will actually come out is given by convention a number 1, and each of its upstream successive states will be numbered accordingly in progressively higher numbers. Okay. So, transfer matrix will be therefore any matrix which will relate this upstream and downstream states. So, we will anyway find out what are these forms of this T11, T12, T21 and T22, but the advantage of this method, if you realize, is that if we simply multiply each of these transfer matrices, we are able to relate P4 V4 with P1 V1, right. P4 V4 is this transfer matrix which basically is identity times P3 V3, but P3 V3 is this transfer matrix multiplied by P2 V2, and P2 V2 is this transfer matrix which again turns out to be identity times P1 V1, right. So, therefore, we can easily write P4 V4 as the multiplication of all these transfer matrices, and here it turns out to be easy because the two transfer matrices in fact are identity, but in general it may not be identity, but none the same you could construct their transfer matrices in some way or the other. But the crucial point is, at the end of the procedure you could relate the upstream state, the final upstream state to the final downstream state simply as a product of transfer matrices, and that is what makes things much simpler to handle. So, as I said in the last lecture that in transfer matrix analysis of these systems, typically you need to have no more than 2 by 2 systems, okay, at least for the simple ones. For more complicated ones you can have more a greater size, but to understand this would be pretty simple, and also to execute this would be pretty simple. So, thus the transfer matrix relating the final upstream state to the downstream state is the product of successive transfer matrices. Okay. That is the key simplification that will happen. Okay. With that, let us now go to derive the transfer matrix for this section within the expansion chamber. We named it as 2 and 3. So, this is station 2, this is station 3, and we understood that we could relate the states at station 3 to the states at station 2 using a transfer matrix of this kind. What the job is to find out these values. The job is to find out these terms T11, T12, T21 and T22. So, towards this end we realize that T11 is equals to P3 if P2 equals to 1 and V2 equals to 0, right. If you put P2 equals to 1 and V2 equals to 0, you will get P3 is equals to T11, right. Similarly, V3 will be equals to T21 if P2 is equals to 1 and V2 is equals to 0, right. So, in other words, if we are able to solve in our usual plane wave analysis or using finite element method or what not, that with this boundary condition that P2 equals to 1 and V2 equals to 0, whatever pressure and velocity we get at station 3 is basically our quantities P11, T11 and T21, right. So, that is precisely what we will do, but before doing that, let us also take the other picture, that is T12 will be same as P3 if P2 is equals to 0 and V2 is equals to 1, and finally T22 will be equals to V3 if P2 is equals to 0 and V2 is equals to 1, right. So, under these special cases, that is either P2 is equals to 1 and V2 equals to 0 or the other way round, that is V2 equals to 1 and P2 equals to 0, if we are able to retrieve what is the pressure and velocity of this upstream point 3, then we should be able to find what is called the propagation matrix between the point 2 and 3, right. So, that is how we will derive it, and towards that end we will call this point as x equals to 0 and this point as x equals to minus a. The reason behind this is that we want a simpler boundary condition. The boundary conditions is given at the station 2 point. So, it is better to give the station 2 a coordinate of 0, because that will turn out much simpler. And between these 2 points within the expansion chamber, we realize there can only be an A wave and there can only be a B wave, each of which are travelling in opposite directions, right. So, we understand that within this region P x will be given as A e to the power minus I k x plus B e to the power I k x, and V x, which is the mass velocity, will be given as A by y e to the power minus I k x minus B by y e to the power I k x, where y is the characteristic impedance in terms of the mass velocities, not in terms of the usual velocity. So, basically C by S is, which is basically constant within the expansion chamber. Remember, we are now working out what is happening in the expansion chamber alone. We are not worried about the other parts. That is what is one very important simplification of the transfer matrix method. It lets you work in individual segments rather than looking at the entire complicated picture in one shot. The next step is pretty simple. What we want to in the first case is that we want P at 0 to be, so we want P at 0 to be 1. That would give us A plus B to be 1. We want V at 0 to be 0, that would give us A is equals to B, right. So, collecting these two, we can always say A equals to B equals to half is the condition that we have for the amplitudes of these two waves which are travelling within the expansion chamber. Now, what remains to be found out is what is exactly the pressure at station 3, which is having a coordinate of x equals to minus L. So, P at minus L is A, which is half, into e to the power minus I k x is minus L. So, this will be e to the power I k L, right, plus B, which is also half, e to the power I k x, x is minus L. So, that makes it e to the power minus I k L, and as you very well know, this quantity is given as cos of k L, right. So, this basically is my T11, because as per the definition T11 is the value of pressure obtained at station 3 if somehow you are able to maintain the value of pressure at station 2 to be equal to unity, but the value of velocity at station 2 is maintained at 0. So, with these conditions we are actually able to solve for and obtain the value of pressure which is given by cos k L. So, therefore, T11 is basically this value. Coming to next, we need to find T21, which is the value of velocity at station 3. So, velocity at station 3 is V at minus L, which is given by 1 by 2 y e to the power I k L minus 1 by 2 y b e to the power minus I k L. So, that would read as 1 by y 1 by 2 e to the power I k L minus 1 by 2 e to the power minus I k L, right. You will know that 2 I sin k L is e to the power I k L minus e to the power minus I k L would give us as 2 I sin k L, right. So, therefore, we could make that substitution and we will have as following I by y sin k L, right, and this would be equals to T12, fine. T21, sorry, T21. Next we need to derive what happens for the entries at the second column of our transfer matrix, and for towards that end we need to solve for the condition that V 2 is equals to 1, but P 2 equals to 0. So, which we will do in maybe I will copy and paste this part. Okay. So, we need to find conditions wherein I need to copy the picture also, I guess. Yeah. And finally, I would copy these two statements. Yeah. So, this is all that we need in the next part of our derivation. So, at x equals to 0, we want P 2 to be 0 this time. So, which means P 0 is given as A plus B, and this has got to be 0 by our requirement, which means that A has to be minus B, right. And V 0 is A by Y minus B by Y, which has to be 1, but minus B is equals to A, which means 2 A by Y has better be equal to 1, which implies that A has to be Y by 2, and that also implies that B has to be minus Y by 2. So, with this as A and B, we would get P x as y by 2 e to the power minus I k x plus minus y by 2 e to the power I k x, and V of x is going to be half e to the power minus I k x plus half e to the power I k x, right. I am replacing A as y by 2 and B as minus y by 2. Since B is minus, the sign of the expression is flipped in the second term. So, that means P at minus L will be y by 2 e to the power I k L minus e to the power minus I k L, and this as we saw is I y sin k L. This bracketed expression is 2 I sin k L. So, therefore, we get P at minus L as I y sin k L, right. Finally, V at minus L is going to be half e to the power I k L plus half e to the power minus I k L, which is cos k L, right. So, therefore, this is T 21 or T 12, sorry, this is T 12 and this is T 22. So, we have found all the 4 entries which are actually called 4 pole parameters of our transfer. We have got all the 4 pole parameters of our transfer matrix. So, let us rewrite the transfer matrix in its grand entirety once again. Thus, cos k L I by y sin k L I y sin k L and cos k L. this is the transfer matrix that we have got. Please note that it is not symmetric. Was it expected to be symmetric? Finite element matrices always turn out to be symmetric. This is not finite element, this is transfer matrix method. Here you are not relating P2 P3 with V2 V3. If you had done so, you would have got a symmetric matrix, but here it is not about relating the pressure states, I mean the pressure variables at both the ends with the velocity variables at both the end. It is about relating the pressure states and the velocity states at both the ends. And also please note that there is no discretization involved here, there is nothing about discrete, this is a complete analytical expression. There is absolutely no errors that we have committed in arriving at this expression. It is a complete analytical exact expression, there is no error at least till this stage. Okay. So, we will denote this by T. So, finally, what we had is that the upstream state at station 4 could be related to the downstream state at station 1 using this very transfer matrix, because the other transfer matrices turns out to be unity in this case, right. In a more complicated situation, which hopefully we should be able to do, we will see that there are other forms of transfer matrices that are possible, right. So, now what we will get is P4 V4 is therefore given by a matrix multiplication of this transfer matrix I y sin k l I by y sin k l cos k l P1 V1. Okay. So, let us redraw the geometry once more. So, here is the input, here we have a muffler and here we have the output. Though in the present example we had taken a simple expansion chamber muffler, in general mufflers can be far more complicated than this simple expansion chamber muffler. But in whatever way we configuration of muffler you have, there are different ways to derive the transfer matrix method, either experimentally or computationally or analytically. But the point is this, you have to finally arrive at this transfer matrix which relates the output of the muffler to the input of the muffler, right. So, finally, the transfer matrix relating the input of the muffler, sorry, relating the output of the muffler, outlet of the muffler to the outlet states, I should say, of the muffler to the input states of the muffler needs to be found. In this case we have already done it, but no matter how general the muffler is, once you get this transfer matrix which relates what happens to the outlet of the muffler to what happens at the inlet of the muffler, the subsequent derivations which we shall do now is again going to be remaining the same, and this is going to give us what is known as the transmission loss. We have already seen transmission loss from the parlance of the regular wave propagation idea. Here we are doing it in terms of transfer matrices, and we will understand that this is much simpler and much more elegant to do. Remember, the geometry that we are dealing with at present is that it is infinite both at the inlet as well as the outlet side at present, right. So, both ways it is running to infinity. If it is running to infinity at the outlet side, you do not expect any reflected wave, there will be only a transmitted wave, right. So, we will call this wave as, let us say, the A1 wave, right, and we will call this wave which is incident as AN wave, which is the incident to the muffler, right, because there are, let us say, n elements and accordingly. In fact, if there are n elements, it will have to be a n plus 1. We will call this n plus 1. Okay. There are a n elements in this which means there are basically n stations. You have to look at the station which is just ahead of this, right. But at present it does not matter whether you call it a n or a n plus 1, does not matter really. But will there be a reflected wave here also? It is going infinity in the inlet side also, but is there a reflected wave that is expected? It should be, right, because if a n plus 1 is not equals to a n, then where has the remaining gone? The remaining has got to be reflected. So, the reflected wave here comes because of the reflection of the muffler, not because of the infinity condition on the left hand side, because the muffler is creating a situation where the transmitted wave is less than the incident wave. So, therefore, the reflection wave the reflected wave has to get generated, and typically as we said, what we are very interested to know is what is this ratio a n plus 1 to a 1, right. The incident wave which is coming and the transmitted wave which is passing past the muffler, and this ratio should be as large as possible, and this is eventually in logarithmic scale is going to give you the transmission loss. So, let us see how from this transfer matrix we can nicely retrieve the this transmission loss characteristics. So, remember the transmission the transfer matrix method works on the states, it does not work on the waves, it is working on the total pressure P 1 which is created by possibly all the waves which are residing in the exit part of the duct. Similarly, P 4 in this case is quantifying the effect of the entire pressure due to both the incident as well as the reflected. But in some way you need to sort of peel out the effect of the reflected wave, and you should be able to be quantifying only the effect of the incident wave. P 4 is the pressure obtained because of both incident A as well as the reflected B wave, right. Both of these waves will combine to give a total pressure P, similarly a total velocity V, but transmission loss quantifies the incident on the inlet side to the transmitted on the outlet side, right. So, we need in some way to do this job for us. On the outlet side things are very easy, that on the outlet side we know P 1 has got to be equals to A 1, right, because on the outlet side there is only one wave, right. So, on the outlet P 1 has got to be equals to A 1, there is no chance that there is any other wave, because anyway it is anechoic termination, right, and V 1 therefore has got to be equals to P 1 by y, but this y is, I will call this as y prime, because I called y corresponding to this expansion chamber, we denoted it is by y. Remember what is the expression for y? Y is given by C by S, and S is the area. So, y corresponding to this is C by S 2, and y prime will be C by S 1, as S 1 is not equals to S 2, y and y prime are not the same. So, P 1 is equals to A 1 and V 1 is equals to P 1 by A prime. So, this is what happens at the inlet side. At the outlet side we will have to do a better analysis. So, at the outlet side we are having, sorry, at the inlet side we are having A n plus 1 and B n plus 1 as the condition. So, again let us take x equals to 0 here for this part of the analysis. So, therefore, P at x for x lesser than 0, we will have P at x to be given by A n plus 1 e to the power minus I k x plus B n plus 1 e to the power plus I k x, and the velocity will be given as A n plus 1 e to the power minus I k x by y prime minus B n plus 1 by y prime e to the power I k x, right. That is the usual expressions that we have. So, what happens at x equals to 0 minus, at 0 minus we will have the quantity P 4, right. This is what is hitting the inlet of the muffler. So, P4 will be given as A n plus 1 plus B n plus 1, and similarly y prime V4 is going to be given as A n plus 1 minus B n plus 1. So, from these two equations it is very easy to recover what is A n plus 1, right. So, A n plus 1 is therefore going to be P4 plus y prime V4, right. This is what we wanted. We wanted to recover the incident wave which is incident onto the inlet side of the muffler in terms of the state variables, and these state variables are already related to the output states. The output states are exactly given by one outgoing wave, outgoing travelling wave. So, therefore, we should be able to do the ratio at this stage. Let us see how it comes through. So, if we open up this expressions, if we open up these expressions, we are going to get P4 is equals to cos k L P1 plus I y sin k L into V1, but then P4 is given as A n plus 1 plus B n plus 1, that should be equals to cos k L. P1 is A1, I y sin k L, V1 is A1 by y prime, right. Instead of V1 I am writing A1 by y prime, and the next equation which reads V4 is equals to I by y sin k L P1 plus cos k L V1, right, and V4 by our calculation here is given by A n plus 1 minus B n plus 1, the y prime that comes on the denominator I will shift it on the other side. So, this is y prime by y, the first term is y prime by y sin k L, P1 is A1, right, plus y prime cos k L. Instead of V1 I have to write A1 by y prime again, right. So, therefore, this y prime is going to, but you get the idea that at this stage at least with these two equations A n plus 1 divided by A1 should be pretty easy to find, right, and that is exactly in logarithmic scale the transmission loss which we had derived as a solution of a 4 by 4 system of equation. But as you see this can be almost done in pen and paper in reasonable amount of time, and we could also interpret the results. Nice interpretation will come out from this analytical formula, which is why we will wait till the next class to give you the interpretation of this result of transmission loss. Okay. Do we have time? I do not think we have. So, we will keep it till here at this point, we will catch it from round about this part.